And welcome back. We are now in the 16th lecture for Math 211. This is the second half of week 8. And we are starting by going over the quiz that was assigned last week. So let's take a look at it. It says the following. A child, this is a quiz for review. It says a child in your second grade class is at the 65th percentile. That the one, or am I looking at a different one?
That's the one.
That's the one. Okay. The 65th percentile. It says, write a brief explanation. So the 65th percentile means, I would say your child is better than 65% of his or her peers in regards to, this test, in regards to whatever. Okay, so, I'm not saying it's taller, he or she is taller, or this or that, but for this specific test or standardized reading test for second graders, your child is better than 65% of his or her peers. That's exactly what the 65th percentile means. Wasn't looking for anything deeper than that, just a sentence explaining what exactly the 65th percentile means. That was question number 1. Hopefully that makes sense.
So could I put the child scored above 65% of the class?
Yeah, that works too.
Okay.
That works too. Make a stem plot to display these quiz grades. So first, let me write them. Let's see. We have 100. We have a 63, a 71, a 78, another 78, a 69, a 93, an 89, a 60, another 69, an 85, a 7. Wow, that person sucked. 90, 91, 29, 90, 55, 39. Oops. 39 and a 50. So we're going to make a stem plot of these. I'm going to use the last digit for the leaves, which means my last category is 10 with a leaf of a 0, so that's 100. 9, 90, 90, 91, 93, 85, 89, 71, 78, 78, 60, 63, 69, 69, 50, 55, 4 with nothing, 39, 29, 1 with nothing, and 0 with 7. And yes, before you ask, those gaps must be there. You can't skip over the 1 and the 4 just because there's no data. And this graph is skewed which way?
Right. Left.
Left. This is a left skewed graph. The tail is on the smaller number side. Okay, if you turn it sideways, the tail's on the left. This is a left skewed graph, skewed left.
Wait, so the direction of the skew is where the least amount of data points are?
I wouldn't look at it that way. The direction of the skew is in the tail. So the big hump is not what's causing the skewness. The tail is what's causing the skewness. Whichever side has the tail, that's the side of skewness. If I had lots of numbers here, all the way here, that would still be the tail side, even though there's lots of numbers there, because the hump's on the other side. Yes, no, maybe so?
Yeah.
Okay.
I resubmitted mine because I accidentally put skewed right. Is that okay? It was like 2 minutes after I realized, so I was like, oh no.
Sure, should be fine.
Okay.
I mean, I haven't looked at them yet. So if you resubmit it, I don't know if I have to kind of go in and find your resubmission, or if it's the second one that's at the forefronts. So if you don't like your grade after I look at it, because I probably won't do it today, just come back to me later, okay?
Okay, sounds good.
All right, then find the 5-number summary. Well, the min is easy. The min is equal to 7. The max is easy. The max is equal to 100. And then let's see how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Is that right? 19? 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13.
Yeah, it's 19.
Yeah, 19. So that means it's a 10th one. That's going to be our Q2. 1, 2, 3, 4, 5, 6, 7, 8, 9, right there. So Q2 is equal to 71. And then to the left of Q2, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 5th one is equal to Q1. So Q1 is 55. And to the right, 1, 2, 3, 4, 5. Q3 is just equal to 90. Hopefully that was clear and obvious. No, shouldn't have been any major difficulties there. Question number 4. A large set of test scores is represented by this cumulative percentage plot. About what percentage of the students got a score of 40 or below. So we go to a score of 40, we go up to the plot, and it looks like to be approximately 20%. B, what score did the student have to get to fall in the 50th percentile? We go up to 50%. We go over to the graph. It looks like about approximately a 65. So that's just reading the graph. Question 5. These box plots show the number of hours slept each night by all teens in a high school over the last week. A. What does the line inside the box represent? That's just Q2 or the median. B. On which day the teens tend to sleep the least? Well, it looks like they slept the least on a Thursday. And there's 2 reasons why. I mean, not 2 reasons why. The reason why is the median is the lowest. But even if you didn't focus on the median and actually went to the very bottom, it's also the lowest. So in other words, there's no reason to say that it was anything other than Thursday. And C, what was the most number of hours slept by any teen during the week? And it looks like there's that asshole up onto the right who got 12 hours. Makes the rest of us feel horrible about ourselves. So I think it's 12 hours. Maybe is it 11, 12?
I put 11 and a half.
I put 11 and a half.
That's fine. That's fine. It's
A lot of the graph things were like not exactly.
yeah. As long as you're a ballpark. As long as you're ballpark, that's fine. Will you take 22% for 4A? What's 22%? I feel like we're bartering here. For 4A. Oh yeah, that's fine. That's ballpark. It's just fine.
68%.
And I put 67 for the 50th percentile for B.
Oh, that's horribly wrong. No, I won't accept that at all.
Okay.
Okay, that's fine. As long as it's close. Okay. All right. Any yeah, so that makes sense. It was a pretty basic quiz, right? I mean, basic if you know the stuff. Nothing's basic if you don't know the stuff. I mean, at the end of the day, things are only basic when you understand it, and things are not basic when you don't. It's only in hindsight we can ask ourselves, okay, was that really basic or not? I mean, like there are things that I know that would take me an hour to do versus things that would take me a second to do. I can do both, but one is a lot more basic than the other. So I based upon my answers, you saw they were pretty much immediate across the board. I mean, yes, the second one required some calculations, but for the most part,
Professor, for that one where you put you to the left,
yeah.
if you didn't place the numbers how you did, you know how you placed them out 7, 29, 39, 55. What if like you put them from least to smallest up top? You say you did that on the top. Just on the top, just when you put them from smallest to biggest and you put skew to the left. I mean, I did put that, but I did a little bit different. From the graph in the bottom, you'll see. I mean, I did put, yeah.
It said skewed left.
Cause I even ended up doing the box plot.
Listen, trust me.
That's how I also got the skew to the left.
If I look at your test and I see the word left anywhere, I mark it right, I move on. So I won't worry
Okay,
too much
perfect.
about it.
Okay, thank you.
Okay, it's not like I'm spending lots of time looking at your answers.
Okay, then we're
Okay.
good.
All
Thank
right,
you.
you're welcome. Any other questions on what we did? Or the quiz, I mean. I did mention that we were gonna have another quiz because we need more quizzes. And I think we were going to talk about which chapter you wanted it on. What chapter was that one on, by the way? Oh,
11.
that was 11. So at this
11.
point, we've done 12, which was on the mean. And 13 is on variability. Did we? I think we finished that one because I think we started 14 already.
Yeah, we started 14.
Yeah, so it's either the mean or variability, or possibly even both. What do you guys think? Which one do you want? Mean, variability, or both? Here, we'll do it in chat. You have three options. On 12, which is on the mean, that's A. Or on 13, or actually we can just do 12, don't do A. So 12, that's chapter 12. Or 13, that's chapter 13 on variability, or both. So I want to see in chat either 12, 13, or both. Go. I'll see what you got. 12, 12, 12, 12, 12, 12, 12, 12, 12, 12, 12, 12, 12. This is close, guys. And we got, there's always that one. There's always that one. So it looks like we'll do it on 13. What do you guys think? Did 13 win? I can't tell.
Perfect.
Perfect. Okay, so the quiz will be on 12. How exciting is that? And today's Thursday. So I think Tuesday is more than enough time. It's 5 days. Okay, so the quiz will be due on Tuesday on chapter 12. Very exciting. I know. I know. It's crazy exciting. Okay, so
Professor, can you sorry, can you put up the answers for chapter 12 homework after class?
yeah. The 11 are the 11 answers up yet? Yeah, 11 answers are up, right?
Yes, those are.
Okay, so I gotta put up, so 12 homework, 12 quiz for Tuesday. And 13, I'll put up 13 homework as well while I'm there, the solutions. And it's time to start chapter 14. So, or not started, I think we started it last time, but we'll continue on it. Okay.
No, we
so-
didn't start it.
Oh, we didn't start it. Oh, but this is my favorite chapter. Okay. Okay, so chapter 14. It actually is weird. Mine doesn't have anything on page 1. Do you guys see anything on your page 1? Hold on.
Yeah.
Oh,
Yeah.
no, I have it now. I have it now. It was delayed. Okay. Chapter 14 is on the normal model, which is without question the most important shape, I guess we'll call it now, in probability and statistics. And what I want to do here is I want to show you something. I'm going to share on my computer. So hold on a second. Okay, so let's get rid of it. Okay, so I'm going to share on my computer. I don't think I've shared this with you. If I have, let me know. Not that, but rather this. Have I shared this with you at all before? This applet, have we ever done any work here?
No.
Okay. So what we have here are we have 8 distributions. And what a distribution means, we'll do the simplest one first, which is number 1. And essentially what it means is we have basically numbers from 1 to 100 or 0 to 100. Let's see here, 0 to 100. And what this is claiming is that every number from 0 to 100 is as equally likely to be picked as any other number. Okay, it's not like number 2 where the bigger numbers are more likely to be picked than the smaller numbers. or 3, where the smaller numbers are really likely to be picked, and the 4 numbers are kind of likely to be picked. The big numbers are kind of likely to be picked, but the ones in the middle are not. Or 4, which is on the edge. On the edge, they're very likely to be picked, but not so much in the middle. For number 1, every number is as equally likely to be picked, almost like you're picking numbers from a hat. And let's say I pick 100,000 numbers. I pick a number, put it back in. Pick a number, put it back in. Pick a number, put it back in. And I collate my data. Roughly how much of each number would you expect to have if every number is as equally likely to be picked as any other number? What would you say? Would you say, would you have more of these, less of those? Well, what do you expect to get as your result? If every number is as equally likely to be picked as any other number, and I do this like 100,000 times, how many times do you think I'm going to get each number?
Once.
Well, there's only 100 numbers, and I pick 100,000 times. How could I get each number only once?
Oh, well, I mean, like, you'd get each like the same amount of times because they're all equally likely.
Okay, so now, do I expect to get exactly the same number of each one or ballpark?
About the same.
About the same. So let's see what happens with this particular simulation. This is an actual example where the computer is picking numbers randomly and then adding them all up and making basically a histogram for how many times each number was picked. They did 100,714 times. And this is what the computer got for their example. Does this seem reasonable based upon what we expect?
Yes.
Yeah.
Sure, seems pretty reasonable, correct? And if we did it again, we get something in the same ballpark again. Wouldn't be the exact same answer, but again, ballpark figure, right? Yes?
Yep.
Okay. Now let me ask you the following follow-up question. Suppose instead of picking 1 at a time, I picked 2 at a time and I averaged them. And I had the computer collate these averages. Rather than the actual picks individually, I had to pick 2 at a time and average them and plot that. What do you think the graph would look like now? Would you think it would look the same? Or would some numbers be more likely than others in this scenario of 2 at a time? What do you think intuitively? And if you're wrong, it's okay to be wrong, but just, think about it. Instead of 1 at a time where they're all equally likely, I do 2 at a time and I average my results. Do I still expect to get each number roughly the same amount of times as any other number?
Yes.
Well, let's think about it. If I pick them 1 at a time, how likely is it to get 0 or to get 100? It's basically 1 out of 100, correct? Because there's 100 choices, or maybe 101 choices. I don't know if 0 counts or not, but let's round it. About 100 choices. And to get a 0 is 1 out of 100. To get 100 is 1 out of 100, correct? You all with me?
Yep.
Now, if I take 2 at a time and I average them, how likely is it for me to get 0 now? What's the only way that I can get 0 if I average 2?
Draw 0 twice in a row.
I had to get 2 zeros. That's the only way to get 0 is my average, correct? So I know that getting a 0 is 1 out of 100, but getting 2 zeros, how likely is getting 2 zeros compared to, for example, averaging and getting a 50? Because there's lots of ways that I can average 2 numbers and get a 50. It could be 0 and 100, 199, 298, 397. There's lots of ways to average to get 50, but not a lot of ways to average and get 0 or 100, right? Yes?
Yeah.
So I would expect intuitively, if I do 2 at a time, that on the sides, it should go down and maybe in the middle should go up. So let's take 2 at a time. I'll increase my sample size to 2 and I'll draw this. Okay, so what it's saying is very unlikely to average and get big numbers or small numbers, very likely to average and get numbers in the middle. That seems reasonable based upon our intuition, right? Based
Right.
upon- Huh?
I
Sorry?
said right.
Right, okay. What if I did 3 at a time? Well, now it's hard, it's harder to have an intuition, but certainly it makes small numbers and big numbers even less likely, correct? Because to get a really small number when I average 3, all 3 of them have to be small, which is a lot less likely than 2 of them, which is itself a lot less likely than 1 of them, right? So let's see what happens with 3 at a time. Or 4 at a time.
So it's becoming more skewed.
Oh, well, actually, it's not becoming more skewed. It's becoming what?
More sloped?
Well, look at your. Look
The
at
metric?
this. You see this? This is the normal model, the bell curve. What is this becoming as a sample size gets, where did it go? As the sample size gets larger, what does my graph seem to be getting closer to?
To the middle. So
Well, to a bell curve.
to the bell curve.
It becomes close to a bell curve. Even though it started very differently, it started very, very uniform. As the sample size increases, it becomes very bell curve-ish. Which of these 8 would you say is the least bell curve-ish of all?
Four?
4, okay, 4 is like the opposite of a bell curve. It's all on the sides and nothing's in the middle. Right? Very unbell curve-ish, right? Let's do 2 at a time and average them. Interesting shape. Let's do 3 at a time and average them. It's kind of weird. 4 at a time. Five at a time. Six. Oh, there it is. I can see a little bell curve now. 7. What do you think about that? Bell curve or not a bell curve?
A bell curve?
Bell curve.
Seems very bell curve-ish, right? So even if we start with a graph that looks very different than a normal graph, than a bell curve, if the sample size gets high enough, everything looks like a bell curve. This is why the bell curve, the normal distribution, is the most, without exception, the most important graph in statistics and probability, because no matter what the underlying histogram looks like, if the sample size gets large enough, it eventually looks like a bell curve. This is why the bell curve, the normal curve, is the most important type of histogram in statistics, which is why it has its own chapter. Chapter 14, the normal model. So a bell curve, if I graph one, make my own little picture of a bell curve, it's not, of course, going to be perfect. Art is not my forte, but it looks pretty close. Okay, the bell curve has a peak, and that peak is the mean.
Professor, I
Yes.
have a question. So this graph looks like the one on the picture for page 1, right? So it's the same one. The normal
Yeah.
and bell is the same.
In fact, I just realized in this class, I don't really use my iPad much. I do it on the screen, don't I? So let's drop the
I like
iPad.
the iPad
and-
better.
Huh?
I like the iPad better personally.
Yeah, but well, is that what everyone wants? They want me to use the iPad?
I like the
Like-
pages better.
You like the pictures better? Oh, we got a fight going. Well, this is a democracy, so let's take a look. Anyone make a choice, either iPad or the way it's been before in chat.
I mean, you could use your Canvas on your iPad and then annotate there on the
Yeah,
front.
you
No
can
way,
download-
I can do that?
Yes.
You can just
What?
download the PDF and input it into Notability.
I mean, you don't even have to download
What?
the app.
What?
You could just,
Wait,
like,
wait. I can do what?
Okay, so on
So you
Canvas,
down-
you sign in and then you click on the file and you annotate it on your iPad.
No, someone said I can do it on Notability. Hold on a second. Hold on, wait,
Yeah,
hold on.
so you download the file and then you input it to
Wait,
Notability.
download my file on my iPad, you mean, right?
Yeah, or if you have the app, you can just click
Yeah,
share.
in the app, you could just
Specifically go
annotate it
to-
easy on your iPad.
Okay, you're all talking. I'm sorry. Not that I don't like hearing all of you, but I can't, I didn't get that. So. I participated the one, sure, I don't care. Okay. What is,
So Lolly, you're muted, so we can't hear you.
I'm,
This is how I have it. So like the PDF, you can really see it.
okay,
But
but how
it's
do I
on-
get, how do I get that onto my iPad though? I am
You
technologically
have to
challenged.
download the Canvas app
Where
On
is
your
that?
iPad.
in the App Store.
So I do that on my iPad.
Yes.
Mhm.
Okay, Apple Store, search Canvas app,
Yes.
nothing's popping up. Canvas,
This Canvas.
just Canvas, search. No, this is not what we're talking about. All right, whatever. We'll figure it out next time because I don't want to waste too much time here. But for now, I'll continue to do it on the computer. But we'll work on this. And of course, it would have been great 8 weeks ago. But hey, what can you do? All right. Anyways, so the normal model. Okay. Many situations in real life can be modeled by a curve that looks like this bell curve, where the majority of data points would be clustered near an average value, near the center of the possible values, and would taper off on each side, eventually becoming somewhat negligible. Height, for example, if you look at the average heights of, let's say, a male American in their 20s, it's probably something like 5'8", 5'9", and you have most people around there. A few inches taller, a few inches shorter, but you don't really have lots of people that are, 7 feet tall or 4.5 feet tall, right? It tapers off on both sides. A lot of things that occur in nature are modeled by curves like this. IQ, intelligence quotient, is modeled by a normal curve. Scores on tests are usually normal. Weight is normal-ish. There's many things that are normal. And a normal curve essentially has two characteristics of it, which tell us which of the infinitely many normal curves we're dealing with. One is where the center is located, where the mean is. Every normal curve has a mean. Now I guessed wrong because it told me that the mean here was 1011, which is more about there. So the mean in this one is 1011. That's the average. That's right in the center. And it claims that the standard deviation is 216. Now, if I start at 1011 and I go to the right 216 or the left 216, 1011 plus 216 is 1227. So 1227 would take me to about there or so. And if I go to the left, 1011 minus 216 would take me to about 795, would take me to about there or so. Now I want to grab these, select, I want to move this up to there, and I want to move this up to about there. Okay. So This point right here where the first, where one standard deviation is on either side. If I were to focus my attention on only the data points that appear between those 2 points. How do I make it thicker? So if I focus my attention on just the data points that are within 1 deviation of the mean, my question to you is, what percent of the total area under the curve is between those 2 points? Would you say it's 50% of the data points fall between those 2 numbers? 60%, 70%, 80%?
Probably about 70.
Oh, about 70. That's actually a pretty good guess. Anyone else want to guess something? Maybe you guys know the answer to this question even before I give it. Anyone know what the answer should be?
Is it 75?
It's not 75. It's an actual number that is determined from calculus. So the best we can do is really approximate it. But the answer is, and this is not working, but anyways, hopefully you understand what I'm trying to do there. But the answer is that if I want to go 1 deviation in either direction, that's going to cover about 68% of all of my data points. 68% is 1 deviation in either direction. So it's from this number here, 7 whatever, to that number there. That contains 68% of my data. Now, if I were to go 2 deviations out, so twice as much in either direction, would that contain more than 68% or less than 68% of my data?
More.
Well, certainly more. It's got the middle 68% plus more. Right? I think maybe you were answering how much extra I'm going to add to it. Is that what you were answering?
Yeah.
Yeah, so I'm talking about total. From the center, if I go out 2 deviations in either direction, I'm certainly going to have a lot more than 68%, correct? Now, it's not 100%. I don't get everything. I'm still missing some stuff. So does anyone know if I go 2 deviations out, roughly what percent of my data I will cover? Anyone know or guess? What percent is covered by 2 deviations in either direction? Take a guess. What do you think? It's not 100%, obviously. We don't get everything.
So you're talking about where you set those lines?
Yeah, so from here to there, all this stuff here. If
That
I,
almost looks like 98.
oh, 98% is not a horrible guess. So again, it's a calculus, a numerical value, and it ends up being about 95%. And if you go 3 deviations out, you get roughly 99.7%. Now, this is a name. This rule has a name in statistics. Now, I have searched long and hard for why it's called this, and I have not been able to figure it out. But the name for this rule is called the 68, 95, 99.7 rule. That's its name. Can anyone maybe venture a guess why it's called that?
Can you repeat that? What is it? What is it called?
It's called the 68, 95, 99.7 rule.
Because that's the lost the vocabulary word. Give me a sec.
Well, this was my attempt at humor, which nobody appreciated because I didn't get any laughter whatsoever. So I hate you all. But anyway,
It was a little funny.
It was a little.
It's
funny.
based on
Okay.
the percentages.
Yes, it's based on the percentage. I appreciate that. Thank you. Okay, so it's called the 68%, 95%, 99.7 rule because it literally says that if you go one deviation out, you get 68% of the data. And if you go two deviations out, you get 95% of the data. And if you go three deviations out, you get 99.7% of the data. And by the way, these captions are amazing. How do those start? Out of the hotel start. Okay, they weren't so amazing, whatever. All right, so let's keep going. Okay, so it says about 95%. Oh, so here's what I just did. 95% are within two deviations. 99.7% are within three deviations. So let's do an example quick. It says the length of full-term newborn babies are normally distributed with mean 20.5 inches and standard deviation 1.0 inches. Complete the scale on the graph. So what would I put? What number would I put right there in the center? What number is right here? What value?
20.5?
Huh?
The 20.5.
Yeah, this number here is 20.5. It's the number right there exactly in the center. Now, if I go right or left one deviation, I'm going to get to 1 over 20.5 and 1 under 20.5. Now, the question first is, how far is one deviation either direction graphically? Is it to here, to here, to here, to here, to here, to here? I mean, how exactly far is one standard deviation from the mean? And amazingly enough, there's a lovely little trick you can use to find it. And that's as follows. Look at the top of the graph, right here in the center. If you had to pick between an adjective saying that part there looks like a hill or looks more like an inverted hill, like a bowl, either a hill or a bowl, which would you say it is? Would you say that the middle is a hill, or would you say the middle is more like a bowl? What is a better adjective for this part right here?
Hill.
A hill, certainly. And hopefully that was obvious to everyone. Now, if you had to pick an adjective between either a hill or a bowl for the far left and the far right of the graph, here and here, if it's either a hill or a bowl, which of those is more appropriate? Would you say hill or bowl?
Bowl.
So that looks certainly more like a bowl, or at least part of a bowl. So then somewhere in between them, the graph must transition from looking like a hill to looking like a bowl. What point, if you had to pick a specific point to say, up until now, it's more like a hill, but now it's more like a bowl, then where exactly, with your finger, you should be able to point and say, right there, where is the spot would you say it changes from hill to bowl?
Is it right in the middle?
So I'll put my cursor to a random spot and you tell me if you believe that's a good location. How about right here?
A little bit higher
Okay, how about here?
or a little bit more.
How about here?
Right there. Yeah.
Okay, do people generally agree with this, at least ballpark? Yes?
Yeah.
Okay, so that point then, and I'll try to just do a better graph of it. So first, here's the mean, which doesn't look to be in the exact center anyways. Let's move that over a bit. That looks better. And then the standard deviation would be from there to about there, give or take. So let's erase this. So this distance then is one standard deviation, which means this point here would then be 21.5. And if I do the same thing in the other direction, then this point here would be 19.5. That's what they mean by set the scale. Find the center and then find one deviation in either direction. Does that make sense? That's a nice graphical way of finding the point at which you've reached one standard deviation away from the mean. Now, in this particular example, 95% of newborns are between what two weights? Sorry, not weights, what two heights?
The 19 and the 21, or the 19.5 and 21.
So would this be 95% between these? This is only one deviation out in either direction. What number do we assign from here to here?
That's 68, so we'd have to get a second.
That this is only 68%, right? Correct?
Yeah.
We
Oh,
want to
yeah.
go to 95% means we got to go 2 deviations in either direction. Which would be between what two numbers?
Eighteen point five and 22.5.
18.5, which is 2 down, 19, 18, and 22.5. Do we agree?
Yeah.
Yeah.
Okay. Now, almost all newborns are between what heights? Now, this notion of almost all, when we say almost all, we really mean within 3 deviations of the mean. So almost all newborns are between what heights?
17.5 and 23.5.
17.5 and 23.5 inches. Now, I myself have never given birth to a child, nor do I plan it anytime soon. So I am not really familiar with these numbers. Does anyone here have more experience? Are these realistic numbers or is this a contrived example?
It is real.
It's
Mm.
realistic? Okay. All right. So does this make sense for this problem? Questions?
Yes.
Okay. So let's go on then. So here's another one. This is SAT scores. And apparently whatever data this came from, the claim is that the mean is 1011 with a standard deviation of 216. So in my little graph here, my little sketch, what number would I pick right here in the center?
1011.
1011. And how far from the center do I go before I've reached 1 deviation out in either direction? Would this be it?
Be higher.
Here?
I think a little bit higher than that, but yeah,
Here?
somewhere there.
Yeah.
Okay, ballpark. So that will be 1,227. Oops, not two.
Anna, let the cat in.
Yeah, you
Let
go with the
the
cat and go
cat
for
in.
it. Yeah, go for it. But I'd get a dog though.
I
They're
am
much-
so
much better.
sorry.
About what? About having a cat? You should be. Okay, so 95% of scores are going to be between what two numbers? %95 of total SAT scores are between what two numbers? Hmm. Anybody?
I'm a little confused. Where did you get the 1227 from?
Well, do you agree that the mean is 1011
Yes.
and that the standard deviation is 216?
Yes.
So if I go 1 deviation to the right, I'm 216 more than this number here. What number is
Okay,
that?
I see. Yeah, okay, I get it now.
Okay. So 98%, sorry, 95% of scores are between what two numbers?
Would it be 795?
795
Wait,
is,
no, wait. Are we doing? Yeah, 795 there. So
I would say 579 and 1,443.
579 and 1,443 is what I got on my calculator. 2 deviations up, 2 deviations down. And almost all scores are between what two numbers?
$363 and 1,659.
1,659. Now, of course, we know that SAT scores cap at 1,600, or at least they did in my day, then they stopped and they went back again, I think, right? Are they back to 1,600 again? I know there was a time they were 2,400, but I'm pretty sure they went back to 1,600, right? Anyone? You know, you're all
No, they
college
didn't.
age, so, huh?
It went back to 16.
It went back to 1,600. So you have to remember that these normal curves, these models are only approximations to reality. You obviously can't get a score greater than 1,659. In fact, you can't even get a score greater than 1,600. So these are only approximations. And if you look at the plot itself on the top of the page, you see that it's not a perfect curve. It's these little jagged edges because this is actual data. No actual data will ever be a perfect normal curve. But from a mathematical perspective, these are just the numbers that we get. Does that make sense so far?
Yeah.
Okay.
Yes.
So now a total SAT score of say 1230 can be meaningless to many students. So I got a 1230. What does that mean? I don't know. I mean, is that good? Is that bad? What's 1230? So we use a measure of position called such as a percentile, which we've used before. So for example, here, we might say that a score of 1230 puts you in the 84th percentile. What does that mean, the 84th percentile? That means you are better than 84% of the people who took this SAT score, right? Now, on my calculator, I can put in very quickly, it takes me just a couple seconds. I can put in press a couple buttons to get the 84th percentile. What was the mean again? 1011 with an SD of 216. So yeah, I did on my calculator very quickly, couple seconds, and it gave me that the 84th percentile is 1226. So yeah, about 1230. Okay. And I'll show you shortly how to use your calculators to do this as well. But first it says locate this score on the plot above. So let's go back to this plot. Let's locate 1230. Where is 1230 located? It's about right here. Does it seem reasonable as a guesstimate to say that if you scored a 1230, then you're better than 84% of the population? Would that be ballpark what you would guess based upon that plot?
Yeah.
Yeah, certainly seems reasonable. I mean, we know this is 50%. And this looks like a lot more than half of what's left because it's much higher on the left than it is on the right. So this is more than 25%. So it's certainly more than 75%. So I think 85% or so is certainly a realistic value based upon the data. What's the percentile for a score of 1011? What is the percentile for a score of 1011? No calculator needed for this one.
50?
Yes, excellent. It's the 50th percentile. It's right in the middle. If you get a 1011, you're right in the middle. You're in the average. You're better than 50%. You're worse than 50%. You are at the 50th percentile. Awesome. 50th percentile. Is it possible that a score of 1,000 falls to the 20th percentile? Is that possible? That a score of 1,000 falls to the 20th percentile? Let's find 1,000. Right there. Can that possibly be the 20th percentile?
No.
No, not by any stretch of the imagination can anyone ever claim that's a 20th percentile. I mean, 1,011, which is barely next to it's the 50th percentile. You're not going to drop 30% in 11 points. It doesn't make any sense at all. So the answer is no, 100% not. Now, when tests are normally distributed, yes, you can use percentiles. Nothing wrong with using percentiles. But we actually use a different type of measure called a z-score, and sometimes even something called a t-score. And z-scores and t-scores are just easier to work with than percentiles. So let's calculate z-scores. So a z-score, very important definition here. So important that I'm going to box it. I'm going to box this. That's an important definition. A z-score is the number of standard deviations a score falls from the mean. Positive when you're above the mean, negative when you're beneath the mean. Doesn't matter what your actual score is. It's completely irrelevant what your actual score is. All that matters is how far you are from the mean in terms of standard deviations. So let's do an example. The Wechsler Intelligence Scale for Children, the WISC-4, much better than the first three WISCs. The WISC-4 is an IQ test used by the LAUSD. The test is normally distributed, looks like a bell curve, with a mean of 100 right in the center, and a standard deviation of 15. So we go with 15 in either direction to reach the transition point, and then 15 more and 15 more to get the second and third deviations out. The question is, what is a z-score for a child who scores 115? How many standard deviations are you above the mean if you score 115 in this example?
One.
One. You're one standard deviation above the mean. And if you score 70, how many deviations are you below the mean?
Two.
So -2 would be your z-score. And if you scored 100, how many deviations are you above the mean?
0.
0. And if you scored a 110, how many deviations are you above the mean?
0.
Well, you're more than 0, but you're less than 1. So it doesn't have to be a whole number.
So like
Wait,
0.5.
And it's more than 0.5. 110 is right, 105, 110, 115. It is more than 0.5.
0.7.
Ooh, less than 0.7.
0.6.
And more than 0.6. Come on, who's got it? It's more than 0.6 and less than 0.7. Can we get the exact value?
0.75.
0.75? No, it's a less than 0.7. We already said.
How do you get it then?
How do you get it? Well, what's the entire length from here to here?
15.
And how far are we from the mean?
10.
10. So we are 10 out of 15 above the mean. What's 10 out of 15?
Six, 7.
Point
0.67.
6 bar, or just 2/3 if you prefer fractions. Which, by the way, gives us the formula that we're going to use for the z-score. If you recall this example, we have the formula that in order to calculate the z-score mathematically, what you do is you look at your actual data. In our case, we got a 110. you look at the average, the mean, which in our case was 100. That tells you your actual distance from the mean. And then you divide that by the actual standard deviation. That tells you how many standard deviations you are above or below the mean. Make sense? We saw it in the last problem. 110 minus 100 was 10 over 15, 2/3. So what's the z-score for 1500? This is back to the SAT example, by the way. Back to the SAT example. How would I calculate the z-score for 1500?
Would you do 1400 over 15?
Well, remember, these numbers were not for the SAT. These numbers were for whatever example we just looked at, which was the Wechsler intelligence scale. But if we're doing the SAT, we're going all the way back to this one, where the mean was what?
1500 minus 1443 over 200.
Oh, 1443. Where's that coming from?
From the third standard deviation, right? Because it's
Oh.
above.
No. But the z-score, the formula, where did it go? The formula is your data point, which is 1500, minus the mean. What's the mean for the SAT example?
1011.
1011 divided by the standard deviation of the SAT example, which was what?
216.
216. So that gives us how much? Approximately
2.26.
2.26. That tells us that if you score a 1500 on the SAT, you are scoring roughly 2.25 standard deviations above the mean, which very few people get to. Because just getting 2 deviations either above or below the mean is what percent of your data points? What percent of your data points are between 2 and 2 below and 2 above?
95%.
95%. So 95%, forget about reaching 2 or 2.26, 95% are just between -2 and 2. And then you have the ones that are way down below on that side. By the way, how much is that percent? If 95, will have the worst bell curve I ever drew in my life. If you draw, whatever. If 2 deviations is 95%, then how much is here past 2 deviations, but only on the left side? What percent will be in there?
2.5.
Yes, good, excellent, 2.5%, because if 95% is in the middle, then you have 5% left over, 2.5% on either side. So this is 2.5%. So just getting to a 2 is already better than 97.5% of the population, let alone 2.26, which is even further. So you're like better than probably like 98% of the population to get a 1500. But what do I get to get a 940? What's your z-score if you got a 940? Is that a good score, 940? What's your z-score?
I got a negative number.
Yes, because you're below the mean. 940 minus 1011 divided by 216 gives you what?
Negative 0.33.
Negative 0.33, which means you fall 0.33 or about 1/3 of a deviation below the mean. I don't care 940. Hey, my score was 940. Okay, what does that mean? Oh, I was 1/3 of a deviation below the mean. Okay, that's where you are. Gotcha. The actual score, you only understand from the context what it means if you know all your values, your mean, your deviation, etc. But z-scores, I don't care. With z-scores, it just tells me how far I am from the mean. That's all a z-score tells you. And quite often, that's all you need. So here's an example. You might have seen these people before. Trust me, this was not my choice to use them. But here we are. So Kim Kardashian is 5 feet 2.5 inches tall, and Kanye is 5 foot 8 inches tall. Men have a mean of 70 inches with a deviation of 3 inches, and women have a mean of 65 inches with a deviation of 2.6 inches. Are either of those two unusually short? So to answer a question like that, you obviously wouldn't say, oh yeah, a woman is short when you compare her to men, because their distributions are different. So if I was asking, is Kanye short, I'd be comparing him to men. If I ask, is Kim short, I'd be comparing her to women. So let's see which one is taller when you look at their gender. What is Kim's z-score? Give me the formula for Kim's z-score. What would it be?
Would it be 62.5 minus 65 over 2.6?
Awesome. Data minus mean over deviation. What do we get for Kim? What do we get for Kim? What's her z-score?
I got negative 0.96.
So she is about 1 deviation below average. And what is Kanye's z-score?
$68 minus 70 over 3.
Which is negative 0.67. So which one is shorter when looked at in the context of their own gender?
Kanye?
Sorry, which one? I'm sorry. I just didn't hear you.
Kanye?
What's Kanye's z-score?
Oh, never mind.
It's Kim.
Kim, right? Kim has a lower z-score, which means she's further away in a negative direction from average, right? Does that make sense?
Yeah.
Yeah.
Okay. Hopefully that's clear for everyone.
Wait, sorry, Kim is taller or Kanye?
I'm sorry?
I missed it. Which one was you said Kim was taller?
Well, no, Kim is shorter. Kim is 5'2.5". Kanye is 5'8".
Shorter than Kanye, but I'm saying in terms of women.
Well, that's the question. So look at those numbers. When you look at Kim in relation to all women and you look at Kanye in relation to all men, which one is further from the center, further from the average, based upon their z-scores?
Kanye.
Kanye is only 2/3 of a deviation down, and Kim is almost a full deviation down. Right? Her deviation is about -1. 1 full standard deviation below the average, whereas Kanye is only about 2/3 of a deviation below the average.
Okay.
Do you see that?
No, but it's fine.
Well, no, it's not fine. -0.96 is about -1, right?
Yeah.
And negative 0.67 is about negative 2/3, right?
Yeah.
So what does this, what do these numbers -1 and negative 2/3 mean? Kim is a full deviation down. Kanye is only 2/3 of a deviation down,
Okay, I see.
right? So Kim is more deviations below the mean than Kanye is by a full third of a deviation.
Okay.
Therefore, when looked at in the context of her own gender, she is shorter than he is.
Okay.
Does that make sense?
Yeah.
Okay. Now this part here, we don't need to worry about because we have calculators, but what if you're stranded on a desert island, you don't have your calculator? So, but looking ahead, it'll take me a little too long to finish this and we're just about done. So we'll stop right here on page 8. I will make sure to put up the homework solutions for 12 and 13, as well as put the quiz up for 12. So, yeah, so that's about it. So are there any questions for today?
No.
All right, well then, have a great weekend. And I'll try to get all those emails answered over the weekends that people have sent. And I will see you guys on Tuesday.
Thank you, Professor.
Thank you, Professor.
You're welcome. Okay,
Have a good one. See you Tuesday.
have a good one. See you then. Okay, bye.
Did you figure out how to get Canvas?
Sorry, say again?
Did you figure out how to get Canvas on your iPad?
Not even close. Well, let me